Hi, my name is Edward Beck. This is my Mod 4 project. We're gonna take a look at some neural networks. Here's a whole bunch of libraries that I imported, um, mainly sklearns, your standard Python fare, and some Keras models that make things much easier. I used a data set from Kaggle, which spanned for 5 years. It had your basic open-close stock prices. I then manipulated the data frame. The target variable is viable, and it basically says whether or not the stock is worth more or less than it was the day before. I extended um, the features out to look at whether or not the stock was going up and down, like a day back, 3 days back, as well as the market in a whole to look at the trend. There's some basic data exploration in here, some statistics. I took the open and looked at it over the whole 5 years, and you can see a nice trend upwards. The first regression I used was the logistic regression. The main reason I did this was to look at the predictions versus the true rates, like true falses and false falses. And the best way to look at that is a confusion matrix. And it appeared that the model had a bit of a bias towards selling the stock compared to buying it. So I used the synthetic minority oversampling technique to balance the confusion matrix out and to have a more balanced effect. Because if not, that bias can come back to really upset the accuracies in the future. The logistic regression, had around about 52% accuracy, and then the other shallow learning models pretty much were about the same, a little bit better. The basic decision tree, and I should say that all the models kept just as they came from sklearn or whatever actually made them, because usually the best optimized there. And so the basic decision tree from sklearn had a 53% or a 55% accuracy, and random forest had by far the best with a 59% accuracy. Everything else fell in between there. Um, XGBoost actually did about the worst at 53.2, which is kind of unusual because in the market it's pretty well, it's got a little bit of prestige behind it and usually does pretty good, but perhaps this data set wasn't too complicated and whatnot. Um, Looking at the receiver operating characteristic, we're looking about the same as 50%, but one would expect that good of a curve here because we are predicting stock prices. Going into the deep learning, I used the LSTM neural network, or the long short-term memory. The reason for that was because of LSTM being able to put a greater emphasis on events that happened in the recent past compared to things that happened at the very beginning of the data set. The train split test was then divided for an 80-20%. There was approximately 600 and 100,000 entries in this data set. And the first model that I used is out of Keras, and I used binary cross entropy as my loss gradient, or my loss classifier, and that's basically tied to the accuracy, and throughout the iterations as the loss goes down, the accuracy normally goes up. And the optimizer I used is ATOM, which is an adaptive momentum estimator. It's a little bit better than the stochastic gradient descent, and ATOM is a combination of adaptive gradient descent and root mean square propagation. And the first, I also implemented an early stopping just in case the learning stopped and the accuracy didn't improve. And I put the first epoch I set was for 15, and the model did pretty good. Got about 55%. And as you can see, there's a nice gradual curve down and our loss, and the accuracy gently increased up. The train and the test were right next to each other, so there wasn't too much or if any overfitting. So looking at the other option, the gradient descent, and I held that for 15 epochs just to be fair, and the accuracy was 53%, which isn't as good as the Atom optimizer, but it's still comparable. I then went on to increase the number of epochs to see if we couldn't increase the accuracy, and as you can see, it's getting a little bit bumpier, and that's generally not a good sign because that could mean that there's some overfitting going on. And as you can see here, the test is like gently going up, or the train is gently going up and the test is kind of all over the place. And unfortunately, our accuracy stayed exactly the same despite doubling the number of times it ran through. The next big thing that was tested or tried was the ReLU activation, and ReLU is the rectified linear unit, and the reason why ReLU is kind of stands out compared to the tangential hyperbolic or even the sigmoidal is because, well, first, you never are dealing with a vanishing gradient with the ReLU, and on top of that, you can stack the layers and go deeper, which is exactly what deep learning is all about. So we use the binary cross entropy for our loss and the atom for the optimization, and I believe in this one, it's just a regular one. Yes, our accuracy went up to about 56% with using ReLU. Here is the loss, and I believe this one, yes, this one is a good showing of what happens when you go for kind of more epochs. You have the test and the train kind of separated a little bit, and you can see right here that the train is overfitting, but then when you bring your test out, the model isn't as good as the train was, and your accuracy is actually decreased a little bit. But I then went on to switch from the binary cross entropy loss to using mean absolute error. And mean absolute error is more to do with predicting the actual stock price, but at the same time, I kind of wanted to just take a look at the mean absolute error loss. Even though I was just predicting a binary loss, the mean absolute error still came in at 52% accuracy. Like, so perhaps like in future, like I could go back or anyone might want to go back and begin to look at predicting the actual price of the stock with the mean absolute error. I certainly wouldn't use as large of a data set, and I began to actually look more into this with ARIMA modeling, but time kind of ran out on me and didn't get too far. But it's another adventure of where to go in the future. And that's all. Thank you.